Fermat's last theorem and Robert D. Carmichael's missed opportunity. My motto? Plain honesty, simple truth, easy understanding, the joy of finding things out for yourself. I would recommend you to look at my other video, the difference of two squares and Fermat-Bateman quadruples of power equal to 1, in order to better appreciate this video. Bateman's unique composite theorem. A Fermat triple, if transformed into its three Fermat-Bateman quadruples by division of its sum and two differences by their answer, and subsequent removal of the three vulgar fractions produced, will, during the process, generate the composite term z to the n times y to the n times x to the n. Fermat-Bateman quadruples by the composite route, where we will show that a Fermat triple z to the n equals y to the n plus x to the n will always produce the composite z to the n times y to the n times x to the n. On this and the next slide we will do it numerically, and since no Fermat triples with an exponent greater than 2 are known, we will take a triple of power equal to 1, for which there are infinitely many. Since we know what the numeric values of z to the n, y to the n and x to the n are at the start, we can obtain the final algebraic equations by direct substitution. 1a, b and c show the Fermat triple in its three possible forms as a summation and two difference equations. 2 shows the three equations as vulgar fractions and all equal to each other and to 1. We have left the exponent 1 symbol off for the rest of the workout. In 3, 4 and 5 we have multiplied through by each denominator in succession to remove the fractions. As a result, the 1 has been multiplied by each term of the triple to give the composite z to the n times y to the n times x to the n, as highlighted in yellow. The three final terms can be arranged in three different ways, which after simplification and rearrangement produce the three Fermat-Bateman quadruples shown algebraically in blue. The three final equations, coloured red, green and blue, and their algebraic equivalents, coloured blue, are the Fermat-Bateman quadruple equations for power equal to 1. As shown, z to the power 1 equals y to the power 1 plus x to the power 1 will, without exception, give the composite z to the 1 times y to the 1 times x to the 1 as an intermediate result. Likewise, when 1 is replaced by n, then z to the power n equals y to the power n plus x to the power n will, without exception, give the composite z to the power n times y to the power n times x to the power n, and highlighted yellow. So what was Robert D. Carmichael's missed opportunity? Well, if you look in The Theory of Numbers by Robert D. Carmichael, Chapter 6, Section 8, on pages 69 and 70, and which can be downloaded free from the Gutenberg project, you will find there a proof of Fermat's last theorem for power equal to 4. Having previously proved that a right-angled triangle can never ever have an area equal to a square, he shows that a right-angled triangle formed by a Fermat equation of power 4 would indeed have a square area. By invoking the three-term composite we have shown to be valid for any and all Fermat triples, together with, you've guessed it, the quarter squares rule. So had he realized it, having proved Fermat's last theorem right for the power 4, he had in reality proved it for all powers up to infinity, including 3. QED. So the supposed need to prove Fermat's last theorem for every prime number to infinity was just mathematician's sleight of hand, and a delusion aimed to fool and bedazzle those of us who, wisely, avoid the illusory abstractions they spin to keep themselves aimlessly employed.